Okay. Yeah, it should be recording now. Yes. Okay. Let us start then. As always, where did we end? So we actually ended in this case study of AlexNet. So we started with studying different coordinate architectures, sort of equipped with the tools that we have came across last week. I think the first two classes. So for example, how does convolution operates, how does pooling operates, and so on. And some tools I have told that I will tell at the end. For example, what is batch norm, dropout, regularization, etc. So just a small idea of, say, dropout I have given, but why it is required, why does it make sense, a batch norm, those I shall come after I have discussed this architectures. So AlexNet was the very first sort of ConvNet. I mean, again, first is within double quotes. It just caused the resurgence of deep learning. But there were, deep nets or deep ConvNets where they are in picture from the late 90s, and LeNet was the architecture that sort of we can say that started it. But at that time, it was way ahead of time that we discussed. So let us actually go and see. Oh, sorry. Let us actually go and see this sort of picture. So these figures will come, as we discuss the different architectures. As we say, sort of conclude discussing about one architecture, this sort of figure will pop up. So let us take some time to basically understand this figure. So this is called the ImageNet leaderboard. So ImageNet is the dataset which is a classification dataset, and I think when I say that LeNet was not ready at that time, LeNet was way ahead of time. One of the reasons was that there was no sort of ImageNet type of dataset. So these deep networks, they strive well with big data, with huge amount of data. With small amount of data, they easily overfit and basically give very poor generalization performance, right? So ImageNet was not there. So ImageNet is a very large scale data. Actually, it is a large scale data because before that, the classification data sets, they were pretty small, like MNIST, 10 classes only. That's also on digits, just grayscale images, okay, 28 by 28, not even natural images, then, or color images. Then there were some other data sets that came, for example, Caltech 101 that has, I think, 100 or 101 classes and so on. But this really was the large scale. It basically was one step up. After that, of course, probably, I mean, they are not called ultra large scale or very large scale, but of course, other higher data sets have come with even more number of classes, more images, etc. But yeah, so ImageNet has 1,000 classes. Each class, I think, had 12 or 1,300 training images and 50 basically test images. So it was huge, 1.3 million training images. Now, yeah, so they actually organized a challenge. So large scale visual recognition challenge, or it was called ILSBRC, where the participants were given access to the training data, that is those for each of those 1,000 classes, those 1,300 images, but not the test data. So test data basically labels, etc., were not given. After the ImageNet challenge was over, it was given. So it was over in 2015, I guess, or 16, or even 17. I don't exactly remember, but not more than 17. Anyway, so then basically what happened is that, okay, you have to come up with your latest and greatest model. You submit it to their server, and their server will evaluate. And that, there was a date. Okay, by that date, they will declare that in this for this year, this is the winner, okay, with this much performance. So you see, This x-axis is different years, so 2010, 2011, and y-axis are these top 5% error rate. So what is 5% error rate? I have explained last lecture. So this was pre-deep learning. Because AlexNet sort of started the resurgence, right? So pre-deep learning, you see that it was 28.2, 25.8, etc. And these were shallow nets, etc. I mean, it did not actually have much parameters to learn and so on. So this was like 25.8, and straight away the AlexNet decrease is almost by 10% or 9%, right? So this is 2012, and if you think or go in 2013, which is a network which we will discuss next, but in very brief, because it is very much similar to AlexNet, just some small tweaks that they added. But you see that decreases from 25.8 to 11.7, so almost halved the top 5% error, right? So within 2 years that happened, and that was, I mean, it was getting sort of saturated this time. I mean, we have not, sorry, one second, I forgot to, yeah, sorry for that. Let me actually make it silent. Yeah. Yeah, again, so it was sort of getting saturated. There were those shift features, then SVM, many other like classical ideas, but I mean, it was not classical at that time, but in 10 years time line we are saying that those are classical ideas. But anyway, that's how basically research happens. So but you see that within 2 years this much improvement happened, and as we will go ahead, we'll see that it went further and further. I mean, less further and further. And the interesting thing is that human error rate is 5%. So I mean, 1,000 classes. Actually, this was an experiment done by Andre Karpathy himself. So he sat for 1 week and tried to train himself with these 1,000 classes and see. But of course, I mean, it was done on small scale with, I think, 50 images or so. He trained himself and then tried to and gave it to his lab mates also. I think 5 or some other humans also did. But it was like 5% was the top 5 error rate for human. But actually, depend. I mean, that is sort of taken as the with some salt, again, pinch of salt. I mean, that is taken as the human performance. But you see that in starting 2015, I mean, it has sort of beat the human. But yeah, again, this has to come with a pinch of salt. Anyway, there are these number of layers, etc., that we will, I mean, these things we will basically come when we discuss them more. I mean, these coordinates, I mean, the architectures. Let us go ahead. So this is the ImageNet leaderboard I described. I will probably not give so much time when I will, sorry, like flash this slide once. I mean, again, after each of these description of these networks. Okay, now next was 2013. So JDEFnet, it is Zeiler and Fargas. So Matthew Zeiler and Rob Fargas from NYU, they actually had or made some changes in AlexNet, and they basically got this 11, I mean, reduced the 16.4 error rate to 11.7. So let us at least briefly see what are the changes and how basically, I mean, how did they come with the changes? That is sort of given in their paper, which we briefly discussed last part. So the visualization and so on. So doing such visualization, they saw that some of the filters are dead, sort of. I mean, it is not learning any weight, so all are zero. So they basically tried to see that, okay, if you change the size of the filters, what happens? Then they saw that, okay, no, most of the filters are not dead. So that sort of, again, very briefly I'm telling, but that paper is a little convoluted, but if you try to read it, it will make things a lot of clear. But the conclusion was that they changed these things. So it is an AlexNet. JDEFnet is an AlexNet, but in Con1, so if you remember, in AlexNet, you had basically in con 1, so here 11 cross 11 filters, and 48 plus 48, that means 96 of them. And then they had this I think 5 cross 5, some I think this size is 3 cross 3, and so on. So but what these guys did is that 11 cross 11, they saw that experimenting with this size, that instead of 11 cross 11 with stride 4, if they do 7 cross 7 with stride 2, that gives this huge performance boost. And another change is that in con layer 3, 4, and 5, not in 2, they did not change the size of the filter there. So I think con 2 was 5 cross 5, and the rest of the other things was 3 cross 3. So, but yeah, the architecture is given in one of the slides earlier. So they changed the number of filters, that is the output channel. So I have discussed what is output channel, what is input channel, right? So 384, 256 to 512, 1024, and 512. So these are like powers of 2, whole powers of 2, and that actually, I mean, among other reasons, one of the reasons is that GPUs are good at basically parallelizing these numbers when the numbers are powers of 2. So that is one of the reasons. And that's why they did it, and so that they basically could efficiently run it. That is, by efficient I mean a little faster. So just incorporating these two changes, they got ImageNet top 5 error from 16.4 to 11.7. So this is basically, oh, this is a typo. Actually, this will be 2022. I mean, I just checked on before the last night of the last class. So this, yeah, I'll correct it. So yeah, so these two changes only basically reduces almost by 5%. So that is JDevNet. So JDevNet is basically AlexNet with these changes. Okay. So this is okay. Before I stop for questions, let me just again flash this leaderboard slide. So it is from 16.4 to 11.7. Now, actually, lots and lots of research groups were interested in it. Not only academic research groups, but different companies also. So actually, in 2013 or 14 rather, two very well-known, one very well-known in academic group and one well-known basically industrial research group, they sought their hand, and it came up with two very famous conv architectures, that is VGG and GoogleNet. So VGG is a visual geometry group from Oxford, University of Oxford, from G. Salmon, Andrew G. Salmon, one of the four figures, founder figures of computer vision. G. Salmon's name probably have all of you have heard. If you haven't heard, just have a look at any of his lectures. The lectures are worth watching actually. If not for anything, just the way he talks and basically conveys the ideas and so on. So VGG came up with something that I mean that we'll discuss next, but that actually reduced the error rate from 11.7 to 7.3. And then GoogleNet. So it sometimes calls GoogleNet sometimes. You see this capital L here. So they actually elegantly combine Google and LeNet. So they sort of paid homage to LeNet. LeNet's list, it is not here, but I mean, we discussed LeNet in one slide at least. That was, I mean, sort of the community tried to pay homage that was due for LeNet, which came at 1998. So it gave this name GoogleNet or GoogleNet. I mean, again, I mean, it is also called the Inception Network. So we will, when we will discuss, we'll see. So the winner was GoogleNet at 2014. So it was it was giving 6.7% top 5% error rate, top 5 error rate. But it was second. I mean, VGG was second, with 7.3. And the number of layers increased. So we saw that in ConNet, there were AlexNet, there were 5 con layers and 2 fully connected layers, and then there was a final classification layer. So there were total 8. In VGG, we'll see soon that they increase the number of layers to 19, and then GoogleNet also used 22 layers. There are intricacies in GoogleNet, so we will discuss both. Then we'll see that, I mean, in 2015, 16, etc., it says, I mean, it's booming 52 layers and so on. So, but yeah, there are catches on those. Just wait, we will discuss. So these are deeper networks. I think I'm missing something, some information I wanted to give, but yeah, let's see if nothing comes to my mind, I will tell. But before I go to describe VGGNet, if there is any question, please raise your hand. Okay, I think, yeah, it was just 2-3 slides that we covered, but yeah, let's go ahead with VGGNet then. So, as I said, VGGNet was from G. Sherman's group. Karen Simonian was the first author. So there are lots and lots of very, very important and good papers that has come from this group, from the same authors. Okay, yeah, so what is the main idea of VGGNet, or what is the main takeaway? It is smaller filters and deeper networks. So in AlexNet or ZFNet, we have seen like 11 cross 11, 7 cross 7, 5 cross 5, all sorts of sizes of filters, right? So they said that, okay, what can be the smallest one? I mean, smallest 2D one. Of course, 1 cross 1 is another idea that we will see later, but it's not sort of a 2D if you think closely about it. So the smallest is, of course, 2 cross 2 or 3 cross 3. So they just took 1 3 cross 3 with different advantages, and they said that there are lots and lots of hyperparameters to play with. So how many layers, or how many, what is the filter size, what are the number of output channels, what is the learning rate, etc., etc. So they said that, okay, let us at least try to be a little uniform, at least to the size of for the size of the filters. So let us just fix the size as 3 cross 3, will not change throughout the conv layers, and let's see what happens. We'll try to make it deep, because that was at 2014. They just saw that, okay, there are 2-3 architectures which used all 8 layers. Why can't we just go more deep? If we, now by that time GPUs have become a little easier to available, and basically a little cheaper. So not only cheaper, the memory wise, it contained, I mean, the GPU RAM is more, VRAM is more, so they can fit like bigger model, more deeper model. So they tried to ask that question. So can we go small and deep? So it actually helped. So in so AlexNet, we had 8 layers. VGG 16 had 16 layers, and there were 2 versions released by them. So VGG 16 and VGG 19. 19 has 19 layers. And I'll come to these figures, like how it is 19, how it is 16, and so on. But before that, they used also this idea that only 3 cross 3 conv with stride 1 and paired 1, and 2 cross 2 max. Oh, okay, I forgot to tell. They also fix the size of the pooling. So you see in AlexNet, they do different sizes of pooling in different layers, with even the overlapping strides in AlexNet. But here in VGG, they said, I will not do overlapping stride. If I am taking 2 cross 2, basically the size of the pooling filter. So if that is okay, let me not draw it so big, maybe. Okay, so if that is, suppose the input feature map at certain point, if you do 2 cross 2, then you are first putting the window here, you are getting the max value, putting it here, then you are putting the window there, getting the max value, putting here the value, max value, then here and here, and the corresponding values are here and here, right? So from a 4 cross 4 input, by pulling 2 cross 2 max pooling with a stride of 2, you are getting 2 cross 2. So you are at least the two-dimensional width and height that is getting halved from if it was like h or w cross h. I think we give the width the first. From here you get w by 2 cross h by 2, right, after pulling. But if you remember your convolution arithmetic slides, what will happen to 3 cross 3 con with stride 1 and pad 1? So if my size is h cross w in my input, and if I add do a con 3 cross 3 with stride 1 and pad 1, what will happen? I mean, what will be the size, new size? So can anybody try to answer? I am just allowing you to unmute. So you can just try to put your con arithmetic slide on, and maybe just have to, you can try to see. I'm just giving a few seconds. The question is again, if it is h cross w input, you are doing con 3 cross 3 with stride 1, pad 1, what will be the output size?
Unchanged.
Unchanged. Yes, that's right, because 3 cross 3 with padding 1 means half padding, right? And we have discussed about what is half padding. And even if we try to do the math, it is like w plus 2p, which is 2 into 1, plus or minus the 3, that is k, divided by 1 plus 1, right? So it is basically w minus 1 plus 1, so it is w, right? So if you do this math, actually it is this, you will find it also, right? So it will remain unchanged. So let us now, I mean, just keep these two facts in mind, and we will then come back to it. So conv actually does not change your size, and pool makes it half. Now, with these changes, and there are a few little tricks, we will come at the end, but these are the major changes. So 11.7 top 5% in ILS VRC 13, that is from ZFnet, it came to 7.3% top 5 in ILS VRC 14. That is that challenge. Again, this citation is ever increasing. There are reasons for that, because you can take this pre-trained model. What is a pre-trained model? Somebody has, say, trained it for you. The GPUs may be that you don't have so many GPUs, so many computes, so much resources, but these guys have it. So they just trained it with very big data set. It allowed the model to basically look at images, which I mean a big number of images or a lot of images to learn the representation out of it. And they just made it available, and you can take it and just use customize it and use it. So how can you customize, how can you use, will come later today itself. But at least what is pre-trained model, I've told. So pre-trained model is they train it on some hugely available, I mean large data set, and make it available. Make it available means the trained weights, the models that are given. Okay, let me actually go to the next slide and see. Okay, so okay, before going to the next slide, I think let me let me actually switch these things so that I have some place. Okay, now let me tell you about the sizes, etc. So what are the number of layers? So 8 layers in AlexNet. So how do you count layers? If you see this image, AlexNet image, so you see that, okay, input of course does not count as layers, but 1, 2, 3, 4, 5, 6, 7, 8, so on. So it's already more than 8. So how are we or why are we calling it as 8 layers? Because when we count layers, the convention is that the layers that are non-learnable, that doesn't have any basically learnable components, they are not counted. So this pool or the softmax is just an activation layer. So there is no parameter there. The parameters, that is W, B, etc., they are all in these layers. Okay, let me just try to use another color, maybe, are in these layers. 1, 2, 3, 4, 5, 6, 7, and 8, right? Out of them, like 1, 2, 3, 4, 5, these are conv layers, and these are fully connected layers. Okay, so again, the convention here is that you tell the size here that, okay, 11 cross 11 and number of filters are 96. Input is, of course, 224 by 224 by 3 that we have seen in our AlexNet architecture. So this 11 cross 11 filter and 96 of them. So and it has some stride, etc. And some padding that is not very clear from here, but we will, when we will go to VGG, that will be given. And then this 5 cross 5, then pool, and so on, right? So AlexNet has its own basically specifications. Now, if we go to VGG, so VGG, if you count, actually, it will come as 16. So I think I can number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So that's why it is 16, called VGG 16, because it has 16 layers. And if you actually take a look at 19, VGG 19, only change is in these 3 sort of blocks. So I can say that, okay, let me give that. Okay, so this is one block, not including the input. This is again one block. This is one block, and so on. They generally take this pool layer as one of the blocks. So let me actually give this. So from here to here is one block, from here to here is one block, from here to here is one block, and so on. In these blocks, this, and this, they just have one additional conv layers. So basically 16 plus 3, it is 19. So that way it is VGG 19, but they actually saw that it does not improve the performance much, and because, but at the, it does not improve the performance much, but it actually increases the computation and the memory requirement of the GPU. So VGG 16 has become so much popular, not VGG 19 so much. But how the memory increases or computation increases will come today on. Okay, now let me try to make it a little zoomed. So this is VGG 16. The input is again 220. That's the same. If you do 3 cross 3 conv 64 again, here, what will be the size if you do 3 cross 3 and 64 filters? So you need to tell me the height, width, and the number of channels there. Okay. So can anybody tell? I am just allowing you to unmute. So what is the output after this? 3 cross 3, half padding, stride 1. What will be the size? Input is 224 by 224 by 3. Anybody? We just discussed about it, right? Half padding, stride 1. Nobody? The convolution arithmetic.
224 by 224 into 64.
Yeah, 224 by 220. That 64 is important actually. 224 by 224. I expected people to give the answer. I don't know why they are not. So you I think just gave it maybe 2-3 minutes back. So 224 by 224, and then 64, because the number of filters here is 64. Okay, so the number of output channels will be 64. Here again, it will be the same. So 224 by 224 by 64. Now, can anybody tell what will be the size of after this pooling layer? So it was 2 cross 2 with stride 2, the pooling window. Anybody? So if the size is H cross W and
112.
Sorry.
Sir, 112 into 112
by
into 64.
Yeah.
Into 64.
Yes, right. So 112, let me just write it here. 112, 112, and 64. Because pooling does not reduce the channel. So this is also important. I mean, we'll come back to this when we discuss GoogleNet. that pooling actually does not decrease the, or basically keeps it same, neither decreases nor increases the number of output channels. Okay, so here it becomes 112 by 112 by 2. Again, if you do the same thing, so since it has 128 number of output filters, so it will be here 112 by 112 by 128, because conv does not reduce the width or height. Then after pooling, it will be 56 by 56 by 128. Now, if you go ahead and do this, I mean, it is fun doing. So here again, 56 by 56. Here it will be 28 by 28, because I mean, after pooling that happens. Then here 14 by 14, and here 7 cross 7 cross 512, right? So this is one thing that you might need to remember throughout. I mean, if you ever work with VGG 16, so 7 cross 7 cross 512, sort of the size of the feature map after the last pool layer. So what is the naming convention, etc.? I will come at the end. Okay, and this FC, I mean, by naming convention, generally people fixed some convention to name these layers. Okay, what is the output? I mean, if you just always say that, okay, it is the output of the layer after the last pool layer or penultimate pool layer, it is hard to remember. So there are some naming conventions that will come. Okay, and then this FC, etc. are there. So there will be, I mean, this has, I mean, this FC has 4096 output neuron, right? As it is shown here. So the output here will have 4096 values, just scalar values. Here also 4096 scalar values. And then this is these are 1000 scalar values, which after softmaxing will just give a, will just give 1000 length probability. Because why 1000? Because ImageNet has 1000 classes. Okay. So any question on this part of the dimension, etc.? If there is, please raise your hand. Okay, but yeah, I mean, the basic idea is that you need to just go through a little bit on the convolution and pooling arithmetic. I think, yeah. Okay, let us go ahead with the next thing. Okay, now this is a very good basically intuition why use smaller filters. So why using smaller filters help? So this is one statement that I am giving, and I'll try to elaborate on it next slide onwards. So stack of 3 3x3 conv stride 1 layers has same effective receptive field as one 7x7 conv layer. So 7x7 conv layer was introduced in ZFNet. Instead of 7x7, I think VGGNet has a stack of 3x3 conv with stride 1. So let us see how this is come into how this comes into being. But before that, we need to like sort of define what is effective receptive field, or what is the receptive field. So what is the effective receptive field of 3x3 conv stride 1 layers? Let us see. But what is receptive field? This is given here. So receptive field is the region in the input space. So I'm just, okay, let me just try to mark the important parts. Region in the input space that a particular CNN's feature or activation value is looking or getting computed due to. Whatever will make more sense, you can just think of it. So let me try to elaborate a little bit. So receptive field, before going to receptive field, let us go and see what is the particular CNN's feature or activation value means. For ease of say understanding, I am just thinking that this is an input image. I mean, it can be another feature value or like activation map, feature map after that is the output after say 1 or 2 conv layers. That can also very well be. But let us try to just say that we are at the very first conv layer. You have input image, and then you have a conv layer which has 7x7 as your K value. That is the width and height of the filter. So you will, from this input image, you will get a feature map after one layer of 7x7 convolution. So this is after one layer of 7x7 convolution. This is the feature map, FMC, let's say. And if you actually judiciously choose the padding and stride, basically half padding and single stride, then this size will remain the same, right? So now the thing is that okay, so how do you get, so this is feature map, so this is the output of the convolution. How do you get, say, this value in the feature map? How can you get it? You find the corresponding pixel value here and put your 7x7 window centered on that, right? So if you put your first 7x7 window, I mean the 7x7 window in the first position centered on this, it will be something like this, 2, 3, 4, something like this. And when you do convolution, that is, you multiply element wise the weights of these basically window and the pixel values. Here, of course, the pixel values are 0, but here you have some weights corresponding to this window and some value corresponding to this pixel value intensity corresponding to this image. And then you do this element wise multiplication, sum it and put it here, right? Put it actually here. Similarly, for this value, you are putting the 7x7 filter centered on here, and you do this element wise sum or element wise multiplication of the weight values and the corresponding pixel intensity values, and then you basically go ahead and put them in this position, in the center position. So now come back to this getting computed due to. So what are the regions, region in the input space that actually is in the is looking at or getting computed due to. So a particular CNN's feature or activation value. So this particular value, what region of due to what region of the input this is getting computed. This is this, right? It does not, I mean, this value does not or is not looking at any of these values, or rather, so to say that these values are not affecting the output here, right? Let me actually try to delete. How can I delete here? Right? So this is not affected by any of these, right? Only these pixel values are contributing to the computation of this, right? So this is called the receptive field. So a receptive field for a 7x7 convolution, one layer, is a 7x7 window, right? Or 7x7 region in the inputs image. Any question on this part? If there is any question, please let me know, because this we will build on the concept. Okay, I'm getting that this is an affirmative thing. Okay, let me go. Okay, so now what is the receptive field of a 3x3 conv layer? Okay, so this is basically again 3x3, because previously it was 7x7. Previously for 7x7, the region that was affecting the computation of this value was 7x7. So for one single layer of 3x3, it will be something like this, a 3x3. Now, if I go ahead and add one more convolution layer, so that's why there was so much white space there. What will happen to, or what is the, suppose this is the input image now, and there are two layers of 3x3 convolution. What was earlier? This was the input image, and this is one layer of 3x3 convolution. Now you have input image here, two layers of 3x3 convolution. Then what region of the input image is affecting this value? For that, you need to go hierarchically, right? So what region is affecting this value from here? It is 3 cross 3 we have seen. And what are the, all these regions are getting computed due to from this input image. So if I just take a note of this, or maybe just take a note of this, so this activation value in this intermediate conv layer, it has this as the receptive field. So only this part is affecting this. And if I just take this, then in the input, this part is affecting this. Similarly, if I go here, it will be just this part affecting this, that is this part. And if I go here, it is this. Now you can compute all of these, not just 4, but you will see that the boundary of overlap for all these 9 values is basically, I'm just changing the color, otherwise it will become clumsy, this. And what is its width and height in the input region? 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So as you add one more layer of 3 cross 3, it is adding 2 value, right? So receptive field is 5 cross 5. And again, remember what is receptive field definition. Receptive field is in the input space. In the input space, which region is affecting the computation of this value, right? So this is the input space. So this becomes 5 cross 5, okay, the receptive field. So 2 layers of 3 cross 3 becomes the effective receptive field is 5 cross 5. Now, if I add one more, you now get the idea. So you just try to find what are these areas. I mean, you actually, in principle, you have to do all of them, but the overlapping area is this, right? And it is 7 cross 7. So the receptive field is 7 cross 7. So this is affected by this. This whole thing is getting affected by this, and this whole thing is getting affected by this. So ultimately, in turn, this is getting affected by this in the input space, right? So the receptive field is 7 cross 7. Now, so this is the basically the statement that I made. Before going to the statement, if I go to this one layer of 7 cross 7 convolution, we see that the receptive field is 7 cross 7. So now try to see the stack of 3 cross 3 conv stride 1 layers has the same effective receptive field as one 7 cross 7 conv layer. So that's what we have sort of visually proved. If you try to come out with a formula, that is also possible. But yeah, I thought that maybe showing it visually is will make more sense. So this statement we have given earlier, and now sort of at least visually we have validated it, that the same effective receptive. Now you can ask that, okay, if I am getting the same effective receptive field, why I am going to use, or what is the advantage of using a stack of 3 cross 3 conv layers instead of 7 cross 7? Are there any other advantage? I mean, it is not, I'm not gaining anything or losing anything in terms of receptive field. Okay, what are we gaining? Let us see. So, but deeper and more non-linearities. So you have 3 cross 3 cross 3 conv layers, and if you remember, after every conv layer we have some non-linearities, and generally we have said that we used ReLU as your non-linearity, but you can use tanh, sigmoid, anything, right? But what this adds is that even if you have the same amount of, I mean, same effective receptive field, clubbing 3 basically 3 cross 3 conv filters allows you to tackle more complexity, because there are non-linearities in between. It is composing 3. So in between there are non-linearities, and you have seen that, okay, if the data set is very complex, there are too much variety between one class or lots of data, you need non-linearity. I mean, if you go back to the perceptron algorithm, perceptron is a very simple algorithm. It doesn't even need a gradient, etc. It has some rule and perceptron learning rule, and that cannot actually solve a non-linearly separable data. So having non-linearity is basically required. So if you can actually incorporate non-linearity, and keep the same effective receptive field, there are two options. One is same effective receptive field without nonlinearity. Another is same effective receptive field but with nonlinearity. Of course, the latter one will work better, right, for complex data. Not only that, there is another thing. So fewer parameters. So you have, for say 7x7 filter, if for the ease of say understanding, I'm just assuming that the number of input channel is C and the number of output channel is also C. So just it is keeping the same, but it will not matter, you will see. So a 7x7 filter will be something like this, a 7x7. I mean, this is 7, this is 7. Then there are these input channels, which is C, and there are the number of C of them, right? Because the number of output channel is this. So you see that the number of learnable parameters is 7 times C times C. So basically 7 square C square. Similarly, for 3x3. It is 3 square C square, but 3 of them because you are stacking 3 layers. So you see it is how many? 49 C square, and this is 27 C square. So you are getting less, you need to learn less number of parameters, right? And you in 3x3 stacked con, and here you need to learn 49 C square. So what are the two advantages? It is more deeper with more non-linearities, capable of handling more complex data, and you are also getting it at the expense of less number of parameters. So there is less chance of overfitting, right? So these are the basically advantages. Okay. Before I go into this part, if there is any questions, please raise your hand. Okay, I see a few questions. I'm asking you to unmute, Rishabh.
Yeah, I mean, we have seen that 7x7 and 3x3 has same effective receptive field. Can you explain this again? Just
okay. I mean, I'm trying to explain, but it's what I explained for last 20 minutes, right? So this is the receptive field of 3x3. So this is getting affected by a 3x3 region in the previous layer. Each of these is getting affected by the corresponding 3x3. So which is this, and so on. Now, if you compute all these 9 values, you will see that the overall region that is affecting this overall region is this, which is 5x5. So this is affecting this, and this is affecting this. So this whole thing is affecting this. So a 5x5 region is affecting this one small value. And if you just basically employ the same idea, then it is 7x7 for one more layer. So 7x7 is affecting one single value in the output. So that is the receptive field is 7x7 for 3 layers of 3x3 convolution. First layer, second layer, third layer. Okay.
Okay, sir.
Yeah. Right. Okay. I see one more question from. Kaushik has. So yeah, quickly. I have to cover it.
Sir, from the good practice perspective, when we initialize these stacked layers, do we initialize them with the same value, or it is better to initialize them with a different?
Yeah, that's a good question. I mean, I think initializing with same value will not matter much, but yeah, I mean, but yeah, I can say what generally people do is that, I mean, they just initialize it with random values. So Gaussian random values. There are other ways like those Javier initialization, etc., etc. But generally with the same value, I have not seen. Okay. Okay, let us go ahead with the few more minutes that we have with this part. I think I have sort of given the idea of this earlier when I asked that, okay, if the input is 224 by 224 by 3, what will be the output size? So let me just try to make it a little big, but it will not fit. Okay, so it is 3 cross 3 cross 64, and people have answered that it will be 224 by 224 by 64. Again, just to repeat, because this is 3 cross 3 half padding with stride 1, the width and height will not change, but the number of channels will be same as the number of channels of the filter. So it is 224 by 224 by 64. So output of first conv layer, which is input to the second conv layer. So this is again, this is the same as the input to the second conv layer. Again, the output of this is then 220. I mean, this means this is 224 by 224 by 64, right? Because it does not change. Again, this half padding, stride 1, etc. Now for pulling, actually this should be yeah, okay. So yeah, the convention I have not come. So pull 2 means basically, okay, so conv 3 means 3 cross 3 and 64 output channels. Again, 3 cross 3, 64 output channels. Pull 2 means 2 cross 2 with stride 2. So it will make it half, as we have seen earlier, 112 by 112, but the filter number of channels will be 64, right? That goes as input to this conv. So it will keep the size, width and height as same, 112 by 112, but the this is 128, right? This number of filters. So 112 by 112, 128. Similarly, if you go all these things, you can compute. So we have done this here. Now let us come to the memory requirement. So after, I mean, so the input is 224 by 224 by 3. So your GPU or the model will it's not model, but at least in the GPU you need to basically input this image. So you need to transfer this, and you need, I mean, the memory of the GPU should be such that it should at least fit this image and other things also. So the memory that is required to store the image is 224 by 224 by 3, that is 150K. It is not in bytes, I am saying. So these many numbers, these many scalar numbers, you have to at least store in the memory for just passing the image to the model. Now, once you pass through the first conv layer, you see that these many numbers are generated, 224 by 224 by 64. So basically these many numbers, again, you need to store, because you have to complete the forward pass. Otherwise, you will not get these probabilities values, right? So you need to store all these, because on this, again, basically the computation will happen. And another one more reason I didn't want to come at this early, but you need to store because in back propagation, you need these forward values somewhere, right? That we discussed. So you need to store. So you need to have these many numbers to store. Similarly, here also. So these are these many numbers you require to store. I mean, and if you just go ahead and do this computation, these red numbers, if you sum, it is these millions. So 15.2 million in a VGG16 model for a 224 by 224 by 3 image. So these many millions, I mean, numbers you need to store. And if I just say that, okay, these are float numbers, I mean 4 bytes memory for each of them. So it actually roughly comes to 58 MB, and that is only for a forward pass. For backward pass, you need to store the gradients also. So it roughly becomes double. Now, this is all about the memory, but what about the parameters to be learned? So these parameters also you need to store, right? So this is not counting the bias. So I'm just, for the sake of simplicity, I'm just not counting the bias. But you see, you know that, I mean, for each filter, you will just have one single bias. So just for the computation, making it easier, I'm just doing that. So in input, there is no parameters. Let's see what are the layers which do not have any parameters. So input, the pooling layer, etc. Right? So these are 0. But what about, say, the first 3 cross 3 cross 64, this one. So this has 3 cross 3 as K values, K cross K, then the input channel, sorry, and so many numbers. So input channel is 3, okay, again. And I mean, for this one. And what are the, so you have 64 such filters. So 3 cross 3 cross 3 cross 64. You see, this is the number. So 3 cross 3 cross 3 cross 64. So these many learnable parameters are there here. Okay. Next time, it is again 3 cross 3, but the input channel is now 64. So 3 cross 3, I think input channel I am giving here. So cross 64, and the output channel is again 64. So these many, and if you do this multiplication, it is coming this. If I go here, what will be the corresponding? Here 3 cross 64, because 64 is the number of input channels, because the input is 64. See, 64 channels, and 128 is the output. So this is 120. So if you again multiply, this is the number of parameters to be learned. So you see that a very interesting thing. Okay, so if you sum these blue numbers, if you just compute and sum these blue numbers, you will see that there are 138 million parameters. So it's huge actually. I mean, so many learnable parameters. Okay, but you remember, going from 7 cross 7 to 3 cross 3 actually reduced it. So you can imagine like what are the number of parameters in AlexNet. Actually, it is less, but yeah, that's for a different region. You can do this computation in AlexNet also. Okay, now the interesting thing is that this memory heavy part, that is the red numbers, are more in the initial part. So you need to store more numbers there, 3.2 million, 3.2 million, etc. But here it is like 25K. 4096 only, etc. at the last layers. I mean, these is the places. Parameters are less in the initial part. So it is like 1728, 36K, etc. But parameters are 102 million in the FC1. I mean, FC, this is called 6, 7, 8, yeah, 6. So, and these are like 16 million, 4 million, and so on. So out of 138 million, you see that 102 million is coming from. So that is, I think, given in the next slide, which when I'm telling that most memory is in early con and most parameters are in late FC. Okay. So this is just this note. Let me see how many slides do I have for completing VGG. I think just 2 more slides. One is just naming convention, and the last one is basically the tricks that they used. So again, so naming convention is actually very easy. You see, these are different blocks as I defined. So this is block 1, this is block 2, and so on. So this is con 1 2 or con 1 1. Con 1 1 1 means first one is the block number, second one is the con filter number. So this is in block 1 the first con filter. This is the block 1 second con filter. In block 2 first filter, block 2 second filter, and so on, right? And then these are like 1 2 3 4 5 blocks. Then these are taken as single blocks, these fully connected layers. So it is the 6th block, and it is called, since it is FC layer, so it is called FC6, it is FC7 and FC8. Now you will sometimes see that, okay, people have taken FC7 features and used in their work, and it did wonders. What does it mean? So if I go back to the term pre-training that earlier I said, so as I said, the need for pre-training. So you as an individual might not have access to GPUs, etc., large computing resources, but these big groups they have. So they generally train it through, say, for ImageNet or even more bigger data sets, and just make this model public. Now, what for your data set? Suppose your data set has only 10,000 images, 10 classes. So if you try to just take this architecture and train it from scratch, that is without using pre-training, this will very well overfit, because you have like 138 million parameters, right? And you don't have so many much data. So what you can do is you can take this model and you just freeze everything else. So till here, you can say freeze. I mean, you can freeze even till here or here. Just people have seen that, okay, for if you have very less amount data, as many as layers, if you freeze, it will do good. So it has learned some representation already by seeing lots and lots, millions of data, right? Now, if you freeze this and now pass, say, one of your images out of this 10,000 through this, what is the number that you get? Here is a vector of 4096 numbers for each of the images. So for each of these 10,000 images, you get these 4096 numbers each. Okay, so 10,000 4096 numbers. So now sort of your 10,000 images are summarized, or sort of let me say that one image is summarized by these 4096 numbers. So sometimes you will see this term encoding. So your one image is encoded by this 4096 number. It's not 224 by 224 by 3, whatever is the value. Not that. It is 4096. So you have sort of summarized, encoded your image. Now you have 10,000 such 4096 numbers. You can use any classifier of your liking, say SVM, random forest, etc., which are known to do better compared to these big models for low data set size, because you have 10,000 images. So this is when people say that, okay, we have taken FC6 or FC7 features. FC6 also gives you 4096 numbers. FC7 also gives 4096 numbers, right? You can just try to take any of them. Even you can take from here, pool. So it was, if you remember, 7 x 7 x 512, and then try to, but it is more than 4096, right? If I am doing it right, yes. So yeah, probably. Now this actually, I mean, gives you a way to basically handle your low size data set. So that's what you call it as fine tuning, right? So you freeze. Oh, okay. One more like option is that you can even just use a FC 1000 layer. Just the FC 1000 layer you will use. So these 4096 numbers will come from the frozen architecture. What is frozen? That is, you are not learning anywhere. Whatever weights the other people have given you, you are just taking it. You are passing your image. You are just taking it sort of a summarizer or encoder, this part. Then you are only learning a classifier, which is a softmax classifier. You are just adding one from these 4096 inputs. You are just adding 1000. So this is 4096. I would say input neurons and 1000 output neurons. Just these weights you learn. Okay, that is called fine tuning. Okay, so you basically can do this fine tuning. Okay, since just I have one more slide, which is sort of summarizing everything. I'm just going ahead in a minute, and then I'll stop for questions. And basically end the class. So it came second in classification, first in localization. What is localization? Localization is not just classifying. If you have, say, a cat here, a dog here, a human here, you need to also put bounding boxes here. That this is where I want to localize the cat, localize the dog, and localize the person. So ImageNet actually runs some localization challenge also. It came first in localization. So we will discuss about localization, detection, segmentation after this topic. Similar training procedure as AlexNet. Basically, that means heavy data augmentation, dropout, batch normalization. I mean, other sort of normalization, etc. No local response normalization. The normalization that was used in AlexNet, that sort of got replaced by batch normalization, which we'll cover later. Yeah, use of 16 and 19 did not have so much improvement. 19 only slightly better, but more memory. Use ensembles for best results, just like AlexNet, and FC7 features generalize well to other tasks, as I said, as the pre-training fine-tuning idea. Okay, let me actually stop this, and if you have any questions, please ask. I see Anupam has a raised hand, so I'm asking you to unmute.
Sir, what is the idea of one hot encoding?
Where did you get that term?
Sir, I have read about it. I just don't know what it means. The idea
I have I think told about it earlier, but yeah, I think it is not related to this lecture. But one hot encoding is basically if you have, say, 1000 classes, you need to tell that, okay, this belongs to, say, cat class. So if you just assume that, okay, cat is your 0th class, say human is your 50th class. So to know that, okay, to tell the model that, okay, my image belongs to the cat class, you just give a single one here in the 1000 leg vector, and everything else as 0. So this is a 1000 leg vector. So that is sort of one hot encoding of an image belonging to cat. For human, it will be in the 50th position, just 1 1. everything else will be 0. So that's sort of a one-hot encoding, because you need to pass that information in a mathematical form to the model. Okay, any other question from anybody? I'll just ask, I mean, basically allow you to unmute. Okay, yeah, Sagar, yeah.
Yes, sir. No, I'm clear with the concept, sir. I just wanted to like point out like the last lecture video has not been uploaded, and
Oh yes,
initially
yes,
is
yes.
uploaded.
You
it will be,
probably
like,
have
good
joined a
reference.
little late this lecture. Yeah, that issue was raised by some other student, and actually it has been uploaded just an hour ago. So I had to join those 2 videos, etc. So it took some time. The slides and the videos are now uploaded. Yeah. Sorry for uploading it late. Any other questions from anybody?